Another oxidation reduction titration, and this time we're going to determine the amount of iron that's present in an iron tablet, and that's what our learning intention is. So like previous titrations, let's have a little look through our reactants. So in our burette, we're going to have potassium permanganate, and the potassium permanganate is of known concentration. In what we'll pipette into our conical flask is a solution of unknown concentration containing iron tablets, which is iron 2 sulfate, and sulfuric acid, which is present in excess, and 25 centimetres cubed is usually enough for that. There's no indicator here because KMnO4 in our burette is a self-indicator, and the endpoint is the appearance of a permanent pale pink colour. In this experiment, to make our solution containing iron 2 sulfate, iron tablets need to be weighed out on a balance. In the lab, they need to be crushed and ground using a pestle and mortar and some dilute sulfuric acid. They're then transferred into a volumetric flask, and the solution is made up to a volume that is required for the experiment. Then the titration just proceeds as normal. As with our titration of the ammonium iron and the potassium permanganate with your iron tablet experiment, dilute sulfuric acid is added in 2 stages. And the first stage, the acid is added to make the iron tablet solution. So it makes it easier for them to be ground, and it also helps prevent the iron from oxidizing with the air from Fe2+ to Fe3+. The second time the acid is added is when we have our solution of iron tablets in our conical flask, and here the acid is added just before the titration is commenced to prevent the premature reduction from Mn+7 to Mn+4, which is the brown precipitate. We want the Mn+2 oxidation state to be obtained. So some sample questions that could come up in this experiment. Why do doctors recommend iron tablets for certain patients? So it's to help treat an iron deficiency in the blood called anemia. Why is it important to use a number of iron tablets in this experiment rather than just one? And it's in order to obtain a solution of sufficiently high concentration to help reduce percentage error in our results. Dilute sulfuric acid is added on 2 occasions during this experiment. Give a reason for the addition. And the acid, as we said in the previous slide, is used to prevent premature oxidation of the iron from Fe2+ to Fe3+, and to help prevent the premature reduction of Mn+7 to Mn+4. The last question then is, why is it important that the burette is rinsed thoroughly after this experiment? And it's because KMnO4 can stain glassware. Other questions that could come up in this experiment would be, why do you read from the top of the meniscus? And that's because KMnO4 is a heavily coloured solution, or a dark coloured solution. Calculations with this experiment usually involve finding the mass of anhydrous iron 2 sulfate in each tablet, then the mass of iron in each tablet, or the percentage of iron sulfate in each tablet. It's important to know that the ratio for this experiment is a 1:5 ratio. So let's have a look at a sample calculation. Again, as with our previous titrations, it's important that we use the first principle methods. You can use the formula method if you wish, but it does not always work and hasn't worked in previous years, so first principles is a better way to go. So, a student dissolved 5 tablets of mass 1.2 grams in dilute sulfuric acid and made it up to a solution of 250 centimetres cubed. 25 centimetre cubed portions of this solution were titrated against a 0.015 molar KMnO4 solution. The average titration figure was 5.75. And here's our equation for the reaction, which shows the ratio of 1:5. And you're asked to calculate the mass of the anhydrous iron 2 sulfate, the mass of the iron in each tablet, and the percentage of iron 2 sulfate in each tablet. So let's work this out. So as with all titrations, the first thing we need to do is we need to find the molarity of our unknown substance. And to do that, we do first principles. So step 1 of first principles is to find the moles of your standard solution in your titra volume. So our formula is moles per litre multiplied by the titra volume and divide that by 1000. So my standard solution is my KMnO4. So I have 0.015 moles per litre. The titra volume for the KMnO4 is 5.75, and I divide that by 1000. And when I do that, I get an answer of 0.00008625. Now, step 2 here is to use your balanced equation to find the moles of the unknown solution in the titra volume. So here I'm looking at the potassium permanganate and comparing it to the iron. And I can see that this is a 1:5 ratio, but I don't have 1 mole of my KMnO4. I have 0.00008625. So I must multiply that answer by 5 to find out the number of moles of iron I have, and that works out to be 0.000431. So the last step is step 3 in first principles, and that's to find the molarity of your unknown solution, and that uses the formula moles by 1000 divided by the titra volume. So here we're going to have the moles, which is 0.000431, because we're looking at the moles of our iron. Multiply that by 1000, and our titra volume for the iron is 25. So if we divide that by 25, what we get is 0.01725 moles per litre. Now, we don't want this in moles per litre, we want it in grams per litre, so we have to multiply this. We want to go from moles to grams, so you have to multiply by the molecular mass. So the molecular mass of our FeSO4 is as follows: 56 plus 32 plus 16 by 4, and that comes out as a total of 152. So I then go and do the 0.01725, and I multiply that by 152. So that gives me 2.63 grams per litre. However, I don't have a litre, I have 250 centimeters cubed. So I need to divide that by 4. So in my solution, I have 0.658 grams of FeSO4 in 250 centimeters cubed. Now, I'm asked, in that 250 centimeters cubed, there is 5 tablets, as you're told, and they ask you for the mass of anhydrous FeSO4 in each tablet. So what I need to do is, now I need to do the 0.658, and I need to divide that by 5. So that means that there is 0.132 grams of FeSO4 per tablet. So that is my answer to part A. So let's move on now to part B. So part B asks me to find the mass of iron in each tablet. So I know that there is 0.132 grams of iron sulfate per tablet. So I need to see how much iron there is. Now I know that my iron is 56 grams. That tells me that there is 36.84% iron in each tablet. So I would need to do the 0.132 grams, and if I multiply that by 36.84%, that tells me that each tablet has 0.049 grams of your iron per tablet. The last step then is part C, and part C asks you to find the percentage of FeSO4 in each tablet. So I know that each tablet, so there is 0.132 grams of FeSO4 per tablet. Now I know that 5 tablets is 1.2 grams. So 1 tablet then must be the 1.2 divided by 5, which is 0.24 grams. So if there is 0.132 grams of FeSO4 in each tablet, if I divide the mass of the FeSO4 per tablet by the total mass of 1 tablet and multiply that by 100, that would tell me that there is 55% of the tablet is composed of FeSO4. So that is your answer to part C highlighted there, and this is your answer to part B highlighted there. So that's a sample exam question or a sample calculation for the iron tablet experiment. That's it for this video. Have a read over the learning intentions to make sure you understand everything we've gone through.